today's CIGRE Ireland webinar, which is focusing on the CIGRE Study Committee B2, which deals with overhead line. So just before we start, can I just remind everyone when the presentations are ongoing to keep your mic on mute and also to keep your camera turned off. And if you have any questions, we'll have time for questions at the end of the presentations, and you can submit your questions in the meantime through the MS Teams chat function. So to start, I'll just run through the agenda for today and some brief introductions to the presenters. So my name is David Tooley, and I'll start today's webinar by giving a brief overview of the work of the B2 Study Committee on overhead lines, of which I'm the Irish representative. So just a bit about myself first. So after graduating from University College Cork, I joined ESB as a graduate engineer in 2008, and I'm currently working now as the Irish representative in the overhead line department. So as regards CIGRE, my current involvement in CIGRE, as I was saying, is as the Irish representative on the B2 committee, which I was appointed to in March 2020. I took over from my predecessor, Tim Condon. And also, I'm also currently a member of one of the working groups in CIGRE. So the working group is the working group 2.67, which deals with the assessment and testing of wood poles and alternative material type poles. So following my presentation, John Lucy will give a presentation on his involvement with in of work 61, which is on transmission line structures with fibre reinforced polymer composites. So John is a design specialist working in the overhead lines design standards team in ESB engineering and major projects. And John joined in about 2015. And since joining ESB, John's been an active member of CIGRE. So in addition to his work in the working group on that he's presenting on today on composites, John's also been a member, or is also currently a member of CIGRE working group 2.77, which is looking at risk management of overhead line networks. So John, a bit of background about John. John graduated from University College Cork with a degree in civil engineering in 2006, and he subsequently obtained a master's in advanced structural engineering from Imperial College London in 2007. So then the third and last presentation of the day will be given by Patrick Porter. So his presentation is on design validation of gap type HTLS conductors through a high temperature field test. So Patrick was lead author on a paper produced on this topic, which he presented on at the recent Paris CIGRE e-session back in August 2020. So a bit about Patrick. Patrick's overhead line design engineer in the HV projects group of ESB engineering major project. So Patrick had joined ESB as a graduate engineer in 2014 after graduating from the University of Ulster, Jordanstown, with a master's degree in civil engineering. And throughout his time, Patrick's been heavily involved in CIGRE. So not only has he been lead author on the paper he's presenting on today, but he was also a lead author on another paper. And Patrick's also currently a member of working group 2.78, which is examining the use of high temperature conductors on overhead lines. I suppose I'm aware that not everyone on the call today is a member of CIGRE, so people mightn't be aware of what CIGRE do and what CIGRE actually is. So I'll just start with a brief introduction to CIGRE. So CIGRE is a global community for the collaborative development and sharing of power system expertise. So what this means is that the professionals from the power system industry across the world share their knowledge and their experiences for the greater good of the industry with regards the production, transmission and distribution of electricity. So CIGRE is a not-for-profit organization which was established in Paris in 1921. So this year is actually CIGRE's centenary year, and I think that they're planning to mark it by a special event this summer to mark their centenary. So at the moment, I don't think it's clear whether this event is going to be an in-person event, a completely online event, or a combination of the two. And that's due to the current COVID situation. It will depend on what they decide in the end. So in CIGRE, there's a total of 59 national committees, of which the Irish National Committee is one. So the Irish National Committee was established in 1955, and I believe the current membership is north of 170 members. So on a global scale, then CIGRE has 15,000 members from 90 countries, and it has those members are from across 12,000 member organisations. So if you're looking to find out more about CIGRE, I've included the link there to the CIGRE website, so there's some useful information there if you want to delve a bit further into it. So CIGRE study committees, and CIGRE organises its knowledge management into 4 main areas. So there's equipment, technologies, systems, and new materials and information technology. So each of these 4 main groups is then subdivided into more specialised topics, which are what we call study committees. So in total, there are 16 study committees spread across the 4 main areas. And you can see that Ireland has a representative on 14 of the study committees. So if you're looking for further information on any of these study committees, you could start by contacting the Irish representative, and the names here given in the slide. But I suppose the focus of today's webinar is on the B2 study committee, which I'm the Irish representative, as I was saying earlier. So just to cover this, what the scope of the B2 study committee looks like. So the field of activities of study committee B2 covers design, construction, and operation of overhead lines. So the scope is quite broad, and it covers a wide range of areas of overhead lines. So I won't read. I've listed the areas of attention here, so I won't read them all out. But I suppose just to scan over them, specific areas of attention would include manufacturing, quality assurance, planning, routing, construction. It would installation. It would cover reliability, availability, condition monitoring, restoration, loading, upgrading, and operating of lines. And it would also look at refurbishment of lines, reuse or redeployment of lines, deterioration of lines, and then dismantling and disposal of lines. So you can see it's quite a broad range of overhead line activities. So the composition of the study committee is shown here on the screen. So we have a chairperson and a secretary, which are these two, which are currently filled by these two gents from Austria. Under that, then we have a regular and observer members. So in the B2 study committee, we have 24 regular members and 14 observer members. So each of those members comes from an individual national committee. So I'm one of the regular members and representing the Irish National Committee. The study committee is supported by these 3 advisory groups. So we have the strategic advisory group, the customer advisory group, and the technical advisory group. So one of the main activities of the technical advisory group is to come up with proposals for new working groups, and to then coordinate the activities of these working groups. So to help with this, the technical activity group is divided into 4 subgroups. So we have one group looking at electrical performance of overhead lines. We have another group looking at tower foundations and insulators. We have a group looking at conductors and fittings. And then we have a 4th group here looking at asset management, reliability, and availability of overhead lines. So under those 4 technical advisory groups, we have you get all the working groups. So I suppose the working groups are really the engine of the CIGRE study committee, in that it's the working groups who want to take all the research into particular topics on behalf of the study committees and that's where the real value is and learnings are with CIGRE. So here I've just given a list of the current active working groups in B2. So I think there's currently approximately 25 active B2 working groups in total. And I suppose just to note that this situation is continuously evolving in that some working groups are finishing up and new working groups are being created. So, to the best of my knowledge, this is the list of the 25 current active groups. So I've also on the slide here, you can see in yellow, I've highlighted the groups which have Irish representation. So you can see there's 10 of the working groups out of 25 have Irish representation, which isn't a bad effort for a country the size of Ireland. And you can also see even the latest working groups are towards the bottom, so you can even see that in a lot of the recent working groups, the Irish representation has increased. So the latest working groups that are coming up, we're getting more involvement from the Irish side. And I just want to say here that I suppose this was the latest information I had as regards Irish representation. So I apologise to anyone if they're a member of one of these working groups and I haven't included their name here. And yeah, I'd also like just to take this opportunity just to congratulate the Irish members for their efforts in not only sharing their technical expertise internationally in these working groups, but I suppose also that they're developing further their knowledge, their technical knowledge through these groups, which can only lead to the betterment of the Irish power system. So I suppose to get involved in working groups, so the responsibility to nominate members to join new working groups is the responsibility of the Irish National Committee. So every now and again, the Irish National Committee will usually circulate an email with the list of the latest working groups that are upcoming, and include in this email a link to the terms of reference for the working groups. So you might just keep an eye out for these emails as they come in, and if you see a working group which interests you, then please do not hesitate to put your name forward to the CIGRE National Committee, who will then consider your nomination. And for people who work in EirGrid and ESB, to put your name forward for a working group, you can contact your company representatives. So in ESB, you can contact Robert Donaghy, and in EirGrid, the contact is Marta Valescudero. And also, I suppose, again, just to take this opportunity to encourage members to get involved in these working groups as they arise. I suppose as the power system industry in Ireland is quite small, so and you don't often maybe get a chance to talk to too many people who work in the same areas as you. So these working groups are a great way to liaise with international colleagues who work in the same field as you, and also to further develop your technical expertise in particular areas which interest you. So the technical brochures. So typically the main output of the working groups is the production of a technical brochure, and the technical brochure will typically provide a lot of technical information on the best industry practices on the particular topic, which was the focus of the working group. So these brochures are available to all CIGRE members for free on the CIGRE online library. They are available to non-members as well, but there's a charge for them, and the charge for the technical brochures is usually in excess of the charge for the annual subscription. So it's well worth being a member for that reason alone to get this information. I suppose from my own experience, I found that these technical brochures they're not only interesting reads, but I suppose I found them to be useful reference documents, which I've actually used in my day-to-day work, as they contain a lot of in-depth information on topics that I've been dealing with. So just on the screen there, you can see this. I think this is some of the recent B2 technical brochures, which were published in the last 3 years, I think. Well, I won't go into detail on them there, but they're all available on the CIGRE online library. Yeah, one of the other activities that Irish CIGRE members get involved in is in the production of technical papers. So CIGRE have a biannual session in Paris, which members can submit proposed papers for acceptance. So the two papers on the screen here are just two papers that were produced by Irish members and presented on at the last Paris biannual session, which was in 2020. So the presenters would usually travel to Paris to give these presentations to an audience of their peers. But this year, naturally, with the COVID situation, or last year, naturally, with the COVID situation, it was carried out virtually. So I think the call for the next CIGRE biannual Paris session, I think the call for papers has actually recently closed, but there will be opportunities to get involved in producing papers at future Paris sessions. So just please, can I just ask the Irish members just to keep an eye out for that and the instructions on how to get involved. So yeah, so this is just a screenshot for the CIGRE online library. So as I was saying earlier, it's a very useful resource. So not only can you find technical papers, but you can find all sorts of information. You can find technical brochures, papers, webinars, and all sorts of other informations of interest on overhead lines in particular, and all the other technical groups the CIGRE deal with. So I think, as I was saying, I'd encourage all members to avail of this information for reference in their day-to-day work. And if you're not currently a member, then I encourage you to sign up in order to benefit from this fountain of knowledge that's available online. Yeah, so that brings an end to my presentation on the overview of the B2 study committee. So if you'd like to join CIGRE, there's further details on joining are available on the CIGRE Ireland website on the link below. If you have any additional questions, suggestions, or want to get involved in the activities of the study committee B2, then don't hesitate to contact me, and my email address there is given below, david.tuohy@esb.ie. So if you have any questions in this presentation, please post them on the MS Teams chat function, and I'll try to get to them at the end of the following two presentations. So I think that brings an end. So I think John, if you're perfect. There, yep. You might take control. I can, yeah.
Yeah, perfect. I'll just grab control there. Perfect. You might just confirm, is that's in full screen, is it?
It is, yeah.
Perfect. Thanks, David. Okay, so first of all, just to say thank you to the CIGRE committee for inviting me to present today. Hopefully people will find the presentation informative. So over the next 20 minutes or so, I'll give a brief outline of the work I've been involved with in regard to working group 2.61, which was on transmission line structures with fibre reinforced polymer composites, so FRP composites. I've broken the presentation into about 5 parts. So firstly, I'll go through, I suppose, how our involvement from an Irish perspective on the working group began. I'll have a look at the technical brochure, which is TB 818. Then I'll give a brief background on FRP materials. I'll then move on to FRP potential uses for transmission line structures, and I'll finish up with some material testing for FRP transmission structures. So looking at the Irish involvement in working group B261. So again, firstly, I'll just give an overview of how the work undertaken within the working group progressed, and hopefully this will give an example of typical timeframes for production of a CIGRE technical brochure. So starting in 2015, Kieran Hughes, who was manager of overhead line design section in ESB International at the time, was the original member of the working group. Kieran moved to a new role within ESB in 2016, so I would have taken over from Kieran as the Irish member on the working group. So probably one milestone, certainly, for those who remember, it was 2017, which would have been the Dublin Symposium, where I suppose a lot of the members would have had to host a lot of the working groups in Dublin. In relation to the technical brochure itself, I suppose 2019, so the majority of the content was completed around 2019 for the technical brochure. And since 2019, the vast majority of 2020 would have been taken up with formatting, editing and reviewing the brochure. And ultimately, the technical brochure was published at the start of 2021. The actual Irish involvement was actually quite high in the working group. So, as I said, Kieran Hughes was the original member, who I took over from. Also, at the commencement of the working group, Rory Geary from TLI was a corresponding member on the working group. And around about the time of the Dublin Symposium, Paddy O'Hora from ESP Networks also joined the working group. So the technical brochure itself, the technical brochure number is, or reference is TB818, and the title obviously is Transmission Line Structures with Fibre Reinforced Polymer Composites. It's available now on the CIGRE portal under the publications section. As I mentioned, the brochure was published at the beginning of 2021. The brochure itself is quite lengthy. There's 240 pages in total. It's quite heavy on images and examples of the use of FRP materials. So I suppose one of the main goals of the brochure was to collate as much information on the topic as possible into one location to act as a good reference point for designers. I won't go through each of the chapters, but just a general summary, there's 22 chapters and 7 appendices in the brochure. So given the timelines, what I'll do for this presentation is I'll just focus on the ones highlighted. So initially I'll just give a background on the composite materials itself. We'll have a look at the structural manufacturing methods. I'll then move on to pole structures, FRP pole structures, which is the majority of FRP pole or structures used at the minute. There is 1 or 2 slides on lattice structures and the use of FRP lattice structures. I'll have a look at the testing of FRP materials, particularly, I suppose, the type testing and pull tests of poles. A brief look at the costing and FRP cost and comparison section. And also there was a survey undertaken by the working group, which is typical of a working group, that usually there is a survey to get some information from members and I suppose focus the topics that are looked at in the brochure. So first of all, just looking at the survey, because it does give some reference point. I'll just get my laser pointer here. A few of the items that came up in the survey, I suppose, looked at, I suppose, specifically for FRP is the longevity and I suppose the service life of structures. I suppose what has come out of the survey is certainly when you look at this this plot on the left, is that there was a lot of don't knows for the service life of FRP pole structures. For the other, I suppose, competing structures, so wood poles, steel poles, concrete and steel lattice, there was a good level of certainty, although the values, there was a good spread on the values, but typically, certainly for the likes of wood poles, the average value seems to be coming in around 40 years, which is debatable, but I suppose it's probably what people consider as the mean value. Typically for FRP pole structures, to answer the question, some manufacturers offer a warranty of 41 years on their product, which is quite high, and typically they would expect the service life of the product to actually be up and around the 80-year mark. The 2 second plots, one in the middle and the one on the right, I suppose, was a survey on the major or perceived major advantages and disadvantages of FRP. Probably the one that jumps out is that people are fairly certain that there's a weight advantage. Also, they're fairly certain that there is an advantage from a corrosion point of view. One of the major disadvantages that seems to be coming out of people's perception of FRP is that there may be a deflection disadvantage. The FRP material background, just to give you a brief overview of the actual material itself. So what is FRP, or fibre reinforced polymer composite? Well, it's material made of primarily two parts. It's a polymer resin and fibre reinforcement. The fibre is where the material gets its strength from, and the resin binds the laminates together and transfers the stress to the fibre. There are other components typically included in FRP, so there's fillers, there's ultraviolet inhibitors, coatings and other additives, but primarily it is the resin and the fibre reinforcement that gives it the properties. Looking at the fibre types, obviously there's a range of fibres now typically available, so I think everyone's aware of carbon fibre, glass fibre or fiberglass, I suppose, as most people would refer to it. There are other fibre types like basalt fibres, aramid fibres, which is Kevlar. I think there's boron fibres as well. But typically it's e-glass, so fiberglass is typically used for overhead line structural applications. I suppose the main reason, while carbon fibre, I suppose, is lighter than e-glass and it has a higher stiffness, it's much more expensive, and some of its properties and process characteristics are not well suited for use in composite utility construction. So typical reasons for using e-glass: high production rates, relative low density, it's heat resistant, good chemical resistance, it's relatively insensitive to moisture. It's non-conductive, but it's not, certainly for overhead line structural applications, it's not a certified insulator. But probably the main reason is the low cost relative to other fibre options. The resin system, I suppose the thing to note on the resin systems is typically there are two major classes of resin. There's the thermoplastic resin and thermoset resin. The thermoplastic resin is pliable or moldable above a specific temperature, so you can reform it, whereas the thermoset resin, it sets and that's it. Typically it is the thermoset resin that's used for transmission structures. Depending on the requirements, typically anywhere between 30 and 70% of the volume could be resin, so I suppose it's vice versa for the fibres. Typically for overhead line structures, you tend to try and keep the fibre content quite high because it gives you the material properties you want. The manufacturing process, probably I've just pulled out the two main manufacturing processes that are used at the minute for making FRP materials for overhead line structures. There are two other primary methods of making FRP material. There's a centrifugal casting method, which I think is used for concrete poles as well. And there's also a resin infusion method, which I think is used for wind turbine blades. But primarily for overhead line applications, it's a pultrusion method or a filament winding method. To go through the pultrusion method, so you have the creels of the fibres which run and are pulled through a resin bath, so they get coated in resin. They're then forced through a heating die and formed into the shape you need and then cut to length. So probably the main thing with pultrusion is high output. It's a continuous process similar to making steel. Whereas with the filament winding process, it's slightly different. It starts off the same. The fibres are pulled through the resin bath, but after that, it's guided onto a spinning mandrel. So probably the big advantage of filament winding over pultrusion is that you can taper the shapes. Because you can taper them, you can stack them, you can modularize the poles themselves, and you can stack them on top of each other, where you can't really do that with pultrusion. They're all the same size. So typically for the pultrusion poles that are on the market, you'd get to about 18 or 19 meters max. Whereas the filament wound poles, you can go up to anything up to even 52 meters. The big disadvantage, obviously, is it's more of a stop-start process in comparison to the pultrusion, where once you have it wound on the mandrel, the mandrel has to be taken away and cured, and the fibres cured so it's much more stop-start. So the filament mount is more expensive, inevitably, than the pultrusion poles. Advantage of FRP structures, as mentioned, I think everyone's probably aware of, there's a weight reduction. Anything up to 25%, or down to 25% of steel weight can be observed. That's probably at the extreme end, though. They're non-conductive, again, although they're not a certified insulator, which is an important point. They have a long service life, so I'm not sure whether you can make out on the image on the top right, but on the actual tag, it was installed in 2009, and the pole itself in the background is as good as day one. The only issue is actually the self-tapping screws, which have started to rust. So I think the learning from this was the actual pole supplier in this case actually switched to stainless steel self-tapping screws. They're inert, so you don't get leaching like you could potentially get in creosote poles, wood poles. They're rot resistant. Again, when compared to wood poles, they're corrosion resistant compared to steel. And probably another one, although not a major issue for the Irish climate, is they're pest resistant. So the last one here is actually, believe it or not, woodpecker holes in poles, which is a big issue in America. Potential uses of transmission line structures. Again, I suppose it's probably dominant. Poles, FRP pole structures are probably dominant in the market. Just to give you, I suppose, a range of uses to date where they have been used. Starting off at the lower voltages, there's an example here in the image in the top left of where they're installing modular poles in back gardens in Australia. So there's an access issue. So one of the main advantages in this situation is that the actual pole modules could be carried in. Moving on to 33 kV in Malaysia, probably a good example of where you could potentially, if it was wood poles, you could have a rot issue. And from a steel structural point of view, you could have a corrosion issue. So there's an improved performance with the composites in those situations. 132 kV in Scotland, which was a fairly dramatic project. They actually used the sky crane helicopter to lift in the complete structures, so quite a rapid construction. So the lightweight nature of the material was quite useful in that situation. 240 kV in Canada. You probably can just make out in the background the steel lattice towers. I think in this case, the reason why the composites were actually put in that location is to reduce the footprint of the structure. And the last example here, 345 at the upper end, just an example, and you can actually see that they're starting to use more and more cross bracing, obviously, because the loading is starting to increase. Pole foundations themselves, so a quick slide on that. Typically, you try to stick to direct embed. It's the cheapest option. But as maybe the soils get poorer or the structures get higher, you start getting into sleeve embedment, where you put a sleeve in the ground and you either fill it with backfill material or concrete. For, I suppose, rocky ground conditions, you can also surface mount the poles. So I suppose the main thing is, depending on what ground conditions you have, there usually is a solution for installing them. Lattice structures, there isn't a whole pile of FRP lattice structures, I suppose, from the research of the working group. The one that did come up is, as I'm shown in this slide, is that in the mid-1990s, a company in California developed and patented an FRP lattice composite system. You probably can just about make out in the middle image that they're actually snap fit connections. The members themselves were pull-throughed, so high volume production, so relatively cheaper than the filament mount members. A 230 kV designed tower was actually full-scale load tested and electrical tested, and 3 of these were actually installed on a line in the US, in California, I think, in 1997. Just some background, the towers are as good as the day they were installed, apparently. They were assembled faster than similar steel lattice towers. There was a weight reduction in towers of about, the towers were about a third the weight of a similar steel lattice tower. The initial material cost, what they found was the initial material cost was actually greater compared to the steel tower. However, the time saved during the assembly put the total installation cost roughly on a par with that of a lattice steel tower. Just one or two slides on cross arms. Obviously, the focus of the presentation up to now has been on poles and lattice structures, but I suppose cross arms are another opportunity to use FRP. So there's 3 examples here. I think again from the US, where they have been using FRP cross arms. Here's another example where actually nearly the entire structure is composite. So you have composite poles, composite cross arms, and composite cross braces. Typically, the connections are actually still steel, but the bulk of the material is composite. Just one or two slides on a cost comparison, which was included in the technical brochure. Probably the main caveat on it is the cost section, I suppose, offers guidance to put a business case together to justify the use of FRP material. The actual figures would probably need to be calculated on a country by country basis and project by project basis, because they are quite specific and sensitive depending on, I suppose, tooling and work methodologies in particular countries, and I suppose climate and ground conditions. Probably the main thing is FRP poles cost more to purchase than wood poles. Typically, the purchase price ranges, they're in between 3 to 5 times a distribution pole, and 2 to 3 times, sorry, these are for wood poles, 2 to 3 times for transmission poles. Probably the main thing that I suppose has to be taken into account in your cost comparisons is what they call a tick-tock analysis. So a total installation cost and total ownership cost analysis should be done. So you're talking about doing net present value calculations and estimating discount rates to take account of the fact that, I suppose, which I've shown in the next slide, where we compare composites, wood poles, steel poles, and I think concrete poles. I suppose what you want to take account of the fact is that the extended service life of the composite poles offers an advantage, but it's an advantage further in time. So you need to do a net present calculation to, I suppose, estimate that advantage. So on this slide, you can see typically the composite pole, there isn't a massive amount of maintenance cost, and it lasts for about 80 years. Whereas with the wood pole, you can see the steps which occur at 30 years and 60 years in this example. Now, again, depending on the country, it could be 20 years, it could be 40 years, but in this example, 30 years was used. So you can see the steps where the pole needs to be replaced. So taking account of that, and also I suppose the slope in the line is where the maintenance cost comes in. You can see that ultimately over the 80 years, this example illustrates that a wood pole is more expensive than a composite pole. Looking at comparing this example where a composite pole set was compared to 110 kV steel lattice tower. So similar to the last one, but what you find with the towers, so they have similar, I suppose, design lives or service lives. But when you compare the steel lattice tower to the composite, there's obviously an optimum span to use the steel lattice towers at. So this example illustrates that. So typically it seems to be which is the black line here, which is in and around the 400 meter mark in this example. And you can see the composite, when you compare it, it is obviously costing less, up to about 200 or 320 meters, and then it goes slightly over. Obviously, where it's costing less further down in the spans, you'd probably be comparing it to wood poles. So I'd probably discount the start of the graph, but certainly up around their optimum spans. So for this composite pole example, it's somewhere between 240 and 300, seems to be about their optimum span, and it seems to be costing roughly about the same as a steel lattice tower with an optimum span of about 400. Material testing of FRP transmission structures. So the technical brochure gives reference material for a whole range of material tests for FRP materials. It's broken into probably three main sections. There's mechanical testing, environmental testing, and electrical testing. So mechanical testing, you'd have abrasion tests, impact tests, tensile and compression tests, and fatigue. But probably the main ones are the full-scale prototype structure tests, type tests. From an environmental point of view, UV accelerated aging tests and moisture tests are probably the big ones. So pull tests and poles. So as the image on the left, the dramatic image on the left illustrates, they do bend. But probably looking at the large displacement in this probably doesn't give the whole picture, because if you did a similar test with a wood pole, you would find that the displacement would be the same, or even the composite is probably slightly stiffer, just ever so slightly stiffer. The poles are obviously benchmarked probably off wood poles, so the properties that the suppliers try to get out of the poles are probably benchmarked off the wood poles, so you would expect a similar performance from a deflection test. Similar to the pole bending test, you can do a full-scale type test of a composite structure. So the example and the image on the right is actually some work ESB International has done with AirGrid, looking at 220 kV composite pole structures. So you can again see, so this is a test station in UCOMSA in Spain. It looks like a small structure, but it's actually about 28 meters tall, this example. So it's quite large. It's just the test station is even larger. So you can see again that there's a significant bend in the pole, but I think this was actually a longitudinal cascade low case. So, but inevitably in this case, it would have passed the type test. Just a quick slide on conclusions. So FRP composite structures offer alternative solutions to traditional construction materials, so wood, steel and concrete. Key benefits, they're lightweight, long service life, corrosion, rot and pest resistance, high dielectric strength, so low conductivity, but again, they're not a certified insulator. They're environmentally inert. Again, typically the purchase price of composite material, or composite poles in particular, is greater than that of competing materials. However, reviewing the total installation cost and total ownership cost can reduce the purchase price disparity significantly. I suppose three takeaways are when to use. Firstly, I suppose when structures don't last as long as they should, so particularly wet locations where you can get corrosion and rot. When installation costs are higher than average, so if you have challenging terrain and ground conditions, and in other high performance applications, such as where you might need high resiliency, so for example, where you have high value equipment on the structures. I think that's the last slide. So I think the questions are at the end, so I think Paddy's up next. So I'm not sure, Paddy, if you're there.
I am, yeah. Just about.
There's a bit of an echo on the line now. Is everyone getting that, are
they? You hear me okay there now?
Yeah, that's perfect. Yeah.
All right, yeah. Grand. You can see it okay there, Dave? Yeah.
Yeah, I can. Yeah.
Good stuff. Grand job. Look, I'll get going then. So, good afternoon, all. So, for those who don't know me, my name is Paddy Porter. I work in the HV projects overhead lines group there in ESB and MP. And so, my own presentation today is going to cover, as Dave mentioned, a paper we submitted for Paris last year, Paris 2020, which did move to an e-session online. So anyone who attended that e-session might have seen the paper. They were all just pre-recorded presentations. That's what I'm going to run through today. So the background to the paper, it really originated from work we did back in 2018, which was a design validation exercise on an in-service 220 kV circuit. And as with any paper, really, following the conclusion and publication of the report, and we gave a presentation on it. We just felt that there was an interesting story there to be told. So we submitted it, just an abstract after the call for papers for Paris, and luckily it was accepted. So, and yeah, the presentation then that I'm going to run through today, look, it's a summary overall of the paper and the key takeaways and points from it. So look, I'll touch on what was the purpose of the test, why was it required, what were the key objectives, a little background then just on HTLS Conductor and why it's used here in Ireland, the desktop research that we undertook as part of the overall test and process, the high temperature test on the day itself then and exactly what that entailed on site, data collection and results. So what were we measuring, monitoring, and what exactly that told us, and just finishing off then with a few quick conclusions. So the background to the test, it was a design validation exercise of the high temperature, low sag gap type conductor, commonly known as HTLS, that's used here in Ireland. So it's just worth noting that throughout the presentation, I'll mention gap conductor or gap type conductor or gap 586. So that gap relates specifically to the design or type of HTLS that's used here in Ireland or has been used in Ireland to date. There are other versions on the market that would be used in other countries, but to date it's just the gap type specifically that's been used here. And that's just the summary of the design shown in the graphic there. So with HTLS conductors, we would refer to them as non-conventional in that they're designed to operate at much higher maximum operating temperatures, so typically upper and above 200 degrees Celsius, whereas the conventional ACSR conductors, which the majority of the transmission grid here in Ireland was constructed with and still operates under today, they would have an MOT of no greater than 80 degrees Celsius. If we look at conductor temperatures in the field then, so on any given day on a typical transmission line, they're typically never any more than plus or minus 10 degrees Celsius away from the ambient temperature on the day, and that would be under normal loading conditions. So the high temperature test, really what we were doing is it was an attempt or a controlled attempt to heat the conductor on a line to at least 50 degrees Celsius above the ambient. And in doing so, then we wanted to monitor or assess the sag tension behavior and basically determine was that behavior in line with the expected theoretical model. So those last two bullet points, they're really, I suppose, a good summary of what the test was and what it was hoping to achieve. So just a quick background on HTLS conductor, the gap type conductor. So it was first introduced back in 2011 as a direct operating option for your conventional ACSR conductors here in Ireland. The key function of I suppose, an operating conductor was to provide a minimum 50% winter rating increase. But also then, very importantly, with any operating conductor, a key selling point of them is that you have no significant compromise in your clearances and or structure loading. So the benefit there to utilities is that you can utilize your existing assets as much as possible where feasible. In total then, we had 4 designs of the gap type HTLS used here in Ireland, 2 at 110 kV and 2 at 220 kV. And I think to date, approximately 10% or around 760 kilometers of the transmission grid has been upgraded, but I would say that figure is likely to be closer to 850, possibly just with work ongoing in the next 12 to 24 months. So when talking about a high temperature test, we're really primarily concerned with the thermal behavior of the conductor. And we know then that behavior is a function of numerous factors. So the conductor material properties, the diameter, the surface condition, the weather conditions in which the conductor is operating, and finally then the conductor electrical current or load. So we know that for a high temperature test, the ideal test requirements would be a a significant load on the line, so we needed at least 2/3 of the rated capacity. We wanted a high ambient temperature, ideally above 25 degrees Celsius. So that was likely to be a midsummer sunny day. And then the last factor then, which is one of the more critical ones, is low wind speeds. And that's just something that we'll touch on in a few slides. So really, having agreed to carry out the test, then the first stage of the overall process was, well, to select a suitable line. So following some initial discussions with EirGrid, Cash Latina 220 kV line in Galway was selected. The line would have been operated back in 2012 with a GAP 586 HTLS conductor. And importantly as well, which was quite useful, is that we had a 3D design model, PLS CAD model, readily available. So that saved us starting from scratch in that regard, is because we would need that design model to carry out the design validation exercise, which we'll touch on later. For anyone just who's not familiar with PLS CAD, so that's the main design software package that we use here in ASB for pretty much all aspects of line design. On the operational side then, EirGrid took into account numerous factors when selecting a suitable line, and I think they settled on Cash Latina for a number of reasons. One of them being its proximity to local generation in that area, the load demands on the particular line at that time, but also then the projected or anticipated system configurations due to outages in the nearby area. So the actual configuration of the transmission grid then on the day of the test, that would have included an outage on the Old Street Woodland 400 kV circuit, and then in addition to that, constraining on generation, a money point and a TINA unit. And those factors combined then enabled 500 MVA to flow on the Cash Latina line on the day of the test. In terms of operational risks then on the EirGrid side, they were further mitigated by ensuring that they had an allowance for additional generation in reserve, an allowance for cross-border trading. Also then we had foot patrols on the line on the day of the test just to monitor any vegetation in close proximity. And finally then the switching, which was carried out via operators at the relevant stations, and it wasn't done via SCADA. So having settled on a line, the next stage then of the desktop study was a span selection exercise. And the reason why this was so important is because in terms of the data collection and how we would collect that and use that to validate the results, this was really going to be focused on one span. It just wouldn't be feasible for that short period of time to gather numerous resources across the line. So we had to undertake a detailed span selection exercise to really find the optimum span for the test. So what was the optimum span? Well, when I mentioned previously about the thermal behavior of a conductor, we noted that there's numerous factors that can influence it. So if we go through each of those, line load, as I mentioned in the previous slide, the grid configuration would enable that, the 500 MVA. Ambient temperature, we were fairly confident of. If you think back to, it was the end of June 2018, so we were in the midst of a mini heat wave, and the forecast was looking very good for that particular week. So we were quite confident in that regard, and that really then left wind, as I mentioned previously, one of the more critical factors. And why it's so critical is, if you take this particular line or any line, it's 40 kilometers in length, traverses various terrain and different altitudes. So the wind speed and the direction could be extremely variable along that entire line route. And a very small change in either can then have a considerable effect on your conductor temperature. So the ideal span for the day of the test and where we would collect our data would seek to minimize as much as possible any cooling effects from wind. So how do you do that? Well, you're talking about sheltered corridors, vegetation, trees, etc. But also we had to ensure that we had a clear, safe, unobstructed corridor for surveying, because there would be numerous people on site the day of the test using various surveying instruments, etc. So we had to ensure that it was accessible. So considering those factors, we developed 6 criteria that are summarized there. And we took those 6 criteria and we applied them, or we assessed each individual span on the entire line and just ranked them accordingly against the criteria. And from that, six spans became apparent as potential candidates for the day of the test. So we followed up each of the 6 spans with a site visit and just further assess them against the criteria. During those site visits, it would have become apparent that some of them just weren't accessible. So eventually we settled on span 57, 58. Which is shown there in their aerial imagery in the photograph. So span 57, 58, it's just north of Loughrea there, near the N56. Relatively long span, 450 metres, so that was a positive. As you can see in the aerial imagery, a bit of a sheltered corridor on the south, on the southeasterly side relative to the prevailing wind direction, so hopefully minimising any cooling effects from wind. And very importantly then, it was also accessible both by foot and by vehicle from a local farm there where we had agreed access with the landowner in question. So following that then, the next stage was to actually carry out the test itself. So it was done on a single day. I think it was a Thursday or a Friday, the 28th of June, back in 2018. So there were a number of us assembled on site the day of the test from ENMP, ESB Networks and EirGrid, carrying out various functions and roles. And the key thing really on the day of the test was to collect the data that we would need to carry out the design validation. And those, I suppose, the 4 areas are listed there that we were monitoring and recording. So the position of the conductors, which we were recording using a laser scanner, the relative sag increase throughout the day, so that was just being monitored using a total station. The actual sag then in real time, so that was being recorded using a true pulse sag monitoring device, and then a thermography inspection, and so that's carried out using an infrared camera. So really point number 1 there in terms of data collection is the critical one, and that's the one that we'll go through in a bit of detail on the next slide. And the reason why that's so critical was without that we couldn't validate the behaviour of the conductors. So EirGrid could load it up, and that would be great. But without recording the position of the conductors throughout the day at various points, we would be unable to validate it. Points 2 to 4 then were really just supplementary, and we produced a report at the time, and they informed the report, and they helped the discussion around the conclusions that we formed, but they weren't really essential. They were just useful to have on site throughout the day and kind of keep us informed. And also then the 1 point there, just accurate metadata. So that's another critical factor. Now, wind speed, wind direction, ambient temperature, it's quite easy to record just when you're dealing with a singular span, in this case span 57, 58. This graph then just shows the load distribution and the ambient temperature on the day of the test. So as you can see, the blue line, it was about 12:30, 1 o'clock, confirmation was given to the NCC to commence the test. So we hit 500 MVA in the line fairly quickly, and that high load then was maintained for about 4 hours. And throughout that time, you can see like the ambient temperature in orange there. So look, we hit the hottest part of the day around 1 o'clock, which was near 30 degrees. So it did prove to be ideal test conditions for the test. On the data collection, look, as I mentioned previously, the critical one on the day was noting or recording the position of the conductors, and that was done using the laser scanner, which you can see in the pictures there. So that's my colleague Dave O'Brien set up underneath the span with the laser scanner, and you can see it's just a portable surveying device. It provides point cloud data. It scans 1 million points per second. A scan will take about 12 or 15 minutes. And in total, we took 4 scans on the day. So 1 pre-test or 1 pre-load, and then 3 scans during the high loading period. And that point cloud data, we then take that and we load it back into our 3D PLS-CAD design model of the line in that particular span. In addition to that, then, as I mentioned, metadata. So look, this is, as I would have mentioned, the factors that can influence or control the conductor thermal behavior, your ambient temperature, your wind speed, your wind direction, etc. So those factors we just recorded throughout the day as well, in addition to the scans. And as you can see from our the 99 picture there, it was a scorcher of a day. I think it was the hottest June day recorded at Shannon Airport in something like 42 years. So it couldn't have gone any better in that regard in terms of ambient temperature and test conditions. It proved to be ideal. The supplementary data collection items then that we were, I suppose, doing on the day, in addition to the laser scanner, The one thing I would say about the laser scanner, although it was critical, and it is critical to carry out the design validation exercise, it doesn't really tell you, in fact, doesn't really tell you anything on the day of the test, because Dave was just recording the scans. Those scans are then saved in the computer, and it doesn't tell us anything about what's happening in real time. So we just thought it would be useful to have a number of our colleagues, particularly from AMS, on site throughout the day, and they were just recording things at various times and noting them down. As I say, look, I won't get into it in detail here, but the paper and the report, etc., would cover these areas in a bit more detail, and the various data that was collected and measured, and how that helped inform the overall discussion. But the first one you see there in the left-hand side, so that's a true pulse device. It measures sag in real time. It's just got a little scope there in the tripod with a handheld camera. You sight onto the attachment points at either end of the span, take a few points along the conductor, and it gives you a sag reading in real time. The lads also then had a handheld infrared camera, which they would use as part of their line condition assessments for maintenance purposes and the like, and they were recording the conductor temperature using that handheld camera throughout the day also. But what we found when we were doing that during the day was, the first one being that we didn't get a temperature greater than 59 degrees with the handheld camera. And then when we compared that to the expected sag of the true pulse device, and we had two separate data sets, they weren't really correlating, and we were getting some discrepancies. And look, that's discussed in a lot more detail in the paper, in the report, but it essentially came down to discrepancies between conductor core temperatures versus surface temperatures, which is quite critical, particularly when you're dealing with high temperatures such as this, well in excess of the ambient temperature on the day. And finally, then, a thermography inspection. So in addition to the handheld camera, then there was a full line inspection done via helicopter, as you can see in the top right-hand side there. So that's just an infrared camera mounted in the front of the helicopter, and it flies through the line and carries out that inspection. The reason for that being is that if you have a line operating under a period of sustained high loading, in this case 4 hours, any areas or locations on the line that maybe are showing increased levels of fatigue, so things like mid-span joints, termination locations, etc., they would then make themselves known during the high loading period. So that was the reason for that, but thankfully there were no issues detected. So having completed the test on site, the next stage then was to begin really the technical or design validation exercise, now that we've collected all the data from site. And that's the first stage of that, is just to calculate your conductor temperatures for each of the 4 scans. And we're using PLS-CAD, the thermal calculator model in PLS-CAD. We have our various inputs: ambient temperature, wind speed, load, etc. And as you can see from the table there, just at the bottom, I think we were 103 degrees Celsius was the maximum calculated conductor temperature, and that was during scan 3. So that was well and above the ambient on the day of it was, I think, around 30 degrees Celsius for that particular span. Just the top row on that table, then you'll probably note that we've included a 5th data set, LiDAR 17. So there was actually a LiDAR survey of the entire line carried out in 2017. And it wasn't really until we were doing up the report that we thought it would be actually quite useful to include this as a separate data set. So if you think about scans 1 to 4, the day of the test being one data set, and then the 2017 LiDAR being a separate one. But what we said that we would do is we would repeat the exercise, i.e. calculate the conductor temperature and include that for comparison purposes, because ideally we should get the same results when we project it out to any temperature for comparison purposes. But you'll note there the 2017 LiDAR, the top row, so the ambient on the day was 5 degrees, calculated conductor temperature was 7 degrees, normal loading conditions on the line, so it's completely, you couldn't get further away from what we had the day of the test, 30 degrees and 500 MVA. But we've included that as part of our comparison as well. So after we've calculated the conductor temperatures, the final step then is to just combine those calculated conductor temperatures in PLS-CAD with the point cloud data collected from the laser scanner. And you're just looking at a 2D profile there through span 57, 58 with your point cloud data loaded in from your laser scanner, your calculated conductor temperature, in this case 103 degrees Celsius. So simply what we do is it's known as a graphical SAG function in PLS-CAD using a finite element sag tension model. PLS-CAD then automatically calculates the sag tension on that particular span. It locks it in or clips it. And what that does then is it allows us to project the conductor out to any weather case for comparison purposes. Now, that could be an everyday case of 15 degrees Celsius. It could be high wind, it could be heavy ice. But for the purposes of the report in the paper, and typically what you would use would be the maximum operating temperature, which we were assuming to be 200 degrees Celsius. So we would have repeated those 2 steps then for each of the 4 scans and also the 2017 LiDAR. Basically, what we would hope to find and what should happen is, regardless of what scan or what data set you're doing, after you do your graphical SAG and project 200 degrees Celsius, you should get pretty similar results for each data set, and that essentially validates your approach and validates the behavior. And that's what we've done in this table. So the table on the top there, we've listed out each of the 4 scans, 2017 LiDAR, and then we've also just included the template SAG for reference. So really we're interested in the right-hand side column, your 200 degrees SAG column. So look, that's where we've taken every data set. We've done the graphical SAG, calculated the conductor temperature. We've projected it out now to 200 degrees Celsius for comparison purposes. And you can see there that there's quite good correlation across all data sets. If we focus on maybe scan 1 to 4 and consider them as one data set, an MOT SAG of 18.2 meters versus 18.4 for the other 3. So that shows good correlation across that. Then considering the 2017 LiDAR, which was a completely independent or separate data under much different loading conditions, ambient conditions, etc. We got 18.3 when we projected that out to 200 degrees, so that shows good consistency across all. The template SAG then in the top row, so that actually refers to the original sagging basis for span 57-58, the day the conductor was installed back in 2012. So that's the template SAG, or the theoretical SAG, that the designer would have assumed when carrying out the original design. And look, 18.9 versus 18.3, 18.4, anything within or close to half a meter shows very good correlation, particularly for a conductor now that's been in service for almost 10 years. So that was certainly a positive note. And essentially validated the approach that we took and the overall behaviour. So that was a good point. The table below it then, that's really just a hypothetical comparison or scenario. And by that I mean that we said, okay, let's just say for argument's sake on the day of the test, the original conventional 600 ACSR conductor was installed on the line. What would have happened hypothetically under those loading conditions and ambient conditions? And what we found is that, well, the maximum operating temperature of 80 degrees Celsius would have been exceeded by nearly 20 degrees. So you're looking at a conductor temperature of 100 degrees or 99 degrees. But more importantly, and I think which probably highlights the benefit of the gap conductor pretty well, is that you're looking at an almost 4 meter SAG increase at maximum operating temperature. So that really highlights the benefit of the non-conventional conductor versus the conventional conductor when you're operating at these higher temperatures. If you think back to one of the earlier slides where I said no significant compromise in clearances, and you can see there that, well, that's essentially what the gap conductor is giving you. Conclusions then. So look, we successfully completed a high temperature test on an in-service major 220 kV circuit. We had a line operating under a period of high load for nearly 4 hours. As you've seen from the slides and the graphics, the conditions on the day really did prove to be ideal, for a high temperature test. I don't think we've probably even had a day like that since. So we were lucky in many ways. We calculated a maximum conductor temperature of 103 degrees Celsius, so well in excess of 50 degrees over the ambient, which we set out to do. when we included then, I suppose, a separate data set, 2017 LiDAR data set, we found quite good correlation across all. So that, in a way, validated the approach and gave us a good benchmark. And I think overall, the paper and the report notes, and hopefully have shown in this presentation today, that the results certainly served as a design validation of the conductor behavior, and they were quite well received by both ESB and EirGrid. So look, going forward, that should enable both of them to exploit that additional capacity that's out there on the 10% of the grid where it's needed. And I think going forward also then, particularly looking forward to 2030 and the ambitious targets that are out there, and the transformation of the grid that's been so widely discussed now, HTLS conductors certainly has a role to play there. Now, whether that's gap type or alternatives, who knows? But I think there's certainly a place for it. So overall, yeah, worthwhile exercise. I think that's everything from me. So thanks for tuning in. I'll pass back to Dave, maybe if he wants to close out the session and take any questions.
Yeah, thanks, Paddy. So just while that was going on there's been a couple of questions in. So there was one from Dave Reedy for John there on, was there any issues with composite poles or FRP poles in relation to forest fires or accessibility?
I can take that there, David. Yeah. So David was just asking in relation to fire, has there been any issues with fire in the composite poles? So just while Paddy was keeping the show going there, I just responded in the chat so people can people can see the response. So I just took a screenshot from the actual report there. So there is a section in the technical brochure on fire. It's probably not a massive one from an Irish point of view, but certainly I suppose it shows the advantage of these technical brochures and having different people from different areas around the globe. Obviously, it would be a big issue in the likes of Australia and maybe California. So it was looked at, and there has been testing done on the composite poles. So there's an image, a screenshot there of some of the testing. And I suppose the general conclusion is that they perform. So the testing was successful. The second question that he kind of asked was in relation to, I suppose, there's more around maintenance in, I suppose, difficult locations. And probably something I didn't touch on is typically with the composite poles in particular is, I suppose, the climbing method is, I suppose the default method is you can always fall back on that they install step bolts. So typically that is what is done with the composite poles. They're climbed using step bolts.
Yeah, thanks, John. Just another point that Dave asked there, Dave Reedy, was the presentation being recorded? So I've just posted the link to the presentation there, so it's on YouTube. So you can feel free to share that with any of your colleagues who mightn't have attended today and who would be interested in the study committee. So does anyone else have any other questions? People can unmute their mics as well if you want to ask a question. We've about 2 minutes left. I think there's one coming there. That's for you, John, from Connor Ryan.
Major difference in needing for painting and corrosion treatments on composite poles. So I suppose the treatment of the composite pole is the resin itself. So while the composite poles can come in different colours, again, I suppose we're kind of focusing on composite poles because that's where the market is at the minute. But I suppose the moisture resistant, the hydrophobic properties and so on is inbuilt into the resin. So you don't need to paint the composite poles. That's probably the big one. I don't know, does that answer the question?
Yeah. Yeah, Connor's happy with that. So, yeah, we have about 2 minutes left if anyone wants to ask any other questions quickly. I suppose if not, I suppose just to wrap up, I just want to say a few thank yous. So obviously, first of all, thanks to John and Paddy for taking the time to prepare and give those excellent presentations. I'd also like to thank Marta Valescudero, Jason Octor, and Valentine Rigoni just for helping prepare and organise today's session, and also just to thank CIGRE Ireland for supporting these webinars. And I think that was all the. Oh yeah, and well, especially just a thank you to everyone for dialing in and showing an interest in the B2 webinar and the presentations that the guys gave. Yeah, yeah, Mark. Okay, so yeah, so thanks again. So we might leave it there, folks, and the link is there anyway to the YouTube for the recording of the presentations if you want to share it to people. So thanks again.